Okay, welcome back everyone. We're going to continue our discussion of one-dimensional motion by looking at instantaneous speed and velocity and acceleration. So what are we hoping to get out of this session? Well, we want to describe straight line motion in terms of both average and instantaneous velocity, and then we want to try to interpret graphs of position, velocity, and acceleration for straight line motion. So last time we talked about average velocity. We connected the points A and B, and we found the slope of the connecting line. But now the question becomes, what happens if A and B get closer to each other? And what you can see is that as A and B approach, we get closer to the tangent of the graph of x versus t. And eventually we get to this point where A and B are effectively the same point. The time difference is effectively 0, and the line is not really a line. It is a tangent to the curve. And so the velocity is represented by the slope of this tangent line. And so we can take a look at this, and we can determine the instantaneous speed and velocity for this particle at point B is if we sketch in a tangent line at point B. Okay, now it doesn't have to be perfect, but maybe you can draw a line a little bit better than me. Okay, let's try that one more time. It kind of goes like that. All right, close enough. So then we look at our values here, and we find the slope of this tangent line, and we're going to have basically -2 over 0.1. So that means that the instantaneous speed, just v average, is just going to be 20 meters per second, but the instantaneous velocity will contain the direction. So that's the negative direction. Okay, so speed and velocity become the same when we're talking about instantaneous. Or another way to think about it is that instantaneous speed is the magnitude of instantaneous velocity. So what about average versus instantaneous acceleration? It's kind of the same idea, that before what we did was we looked at the slope of a line connecting these 2 points on the velocity versus time graph. And again, as these points get closer together, we can talk about instantaneous acceleration. So if c is actually equal to a and b put together, then it's the slope of a tangent to the curve on a velocity versus time graph. And we'll get a little bit more into the math in just a second, but we're just doing this qualitatively for the moment. So here's another view. And we have negative instantaneous acceleration when this curve is concave down. And we're going to have positive instantaneous acceleration when it's concave up, and we will have 0 instantaneous acceleration where the slope is constant. That's an inflection point on this particular graph. So we'll do a couple examples. Okay, so think about an object that's dropped from rest and reaches terminal velocity during its fall. And we're going to say that upwards is positive and downwards is negative. What would the velocity versus time graph look like? Well, terminal velocity just means that it's not getting any faster. And we'll study this in great detail when we do forces, but basically the velocity graph will kind of level off. And it'll level off at kind of an asymptote here, which we call Vt, the terminal velocity. Something like that. Okay, now what if we drop something from rest and it reaches terminal velocity, and we want to look at the position versus time? What would this x versus t graph look like? Well, we want to think about the prior graph, and in that we had a graph that was basically negative for all t. That was v versus t. So we want to remember that velocity was always the slope of this position graph, And so we want to have a graph that has a negative slope everywhere. So kind of like this. And notice that at the end, we just have a constant slope because this velocity graph is leveled off. Okay. Now the other thing that you can do is you can work backwards. So just to kind of recap, if we have x and we take the slope, that's going to tell us v. And then if we take the slope of that, that's going to tell us a. But we can work backwards. If we take the area underneath an acceleration graph, that will give us the change in velocity. And if we take the area of that graph, it'll give us the change in displacement. So perhaps an example or two will help. First, we want to estimate the net change in velocity from 0 to 4 seconds. And I'm going through all of this fairly quickly because I would assume that you've seen some of this before, either in a prior physics course or by taking a look at the textbook. So the net change in velocity, notice that if we take the area of this graph, we are going to get the correct units for velocity, so meters per second squared times seconds, which is meters per second. So in other words, delta V is equal to A delta T. And we can break this up into chunks. And basically we have two triangles that have equal areas. So the total area is going to be equal to 0. We have a triangle right here that has a height of 1 and a base of 2, so it's got +1 area. And another triangle that has -1 area, so it's a total area of 0. So the total change in velocity over this entire 4-second run is going to be 0. It doesn't mean that the velocity isn't changing, it's just that the net change in velocity will be 0. Okay, so let's look at another example. Let's find the net displacement, the delta x, from 0 to 4. And that's going to be v times delta t. And if we break this up into two pieces, or we could do a trapezoid, this is going to be 1/2 times 2 times 2, so that's going to be 2 meters, right? Meters per second times seconds. It's going to give us meters. And here we're just going to have 4 meters, so we have a total of 6. Okay, so that's going to be it for this time. Next time we're going to talk about how to actually calculate instantaneous velocities and accelerations using derivatives.